Hello viewers, Wagadaruna taking you through this tutorial for A-Level Applied Mathematics. And this video I'm going to go through the topic of elasticity. So this video is suitable for students in both Senior 5 and Senior 6 offering principal mathematics as part of their combination. So before we start, let's first look at the course outline. That is the course outline for Math Paper 1, which was covered, and now we are about to finish Math Paper 2, after which we shall go to Physics and A-Level Math Contest. So this today, what is strict is already available on this platform, and in this video I'm going to go through the topic of elasticity. So this has been skipped because it will be covered last. And the books which you'll need at this level are here. So by all means, I encourage you to try always to get them. If you are doing principal mathematics, there should be 4 books. There's Math Paper 1, Math Paper 2, Topical Question Bank, Termly past papers with marking guides. Then for subsidiary math, it is only 1 book which contains everything, notes, past and Termly past papers. Then for physics, there is Physics Paper 1, Paper 2, Topical Question Bank, and their solutions. So for any of these books, contact the author on this contact so that you can get them at a relatively cheaper price. Otherwise, they are available in a number of bookshops in Kampala, though they will be at a relatively higher price than the one you'll get them if you call. So we shall start our topic of elasticity, and the first term to understand is elastic strings. So this topic of elasticity is divided into 2. We have what we call strings and also what we call springs. So they are somehow similar and the formulas used are the same, only that in springs allow compression and extension. They can be stretched and compressed, but strings, they can only be stretched. So that is the only difference, but all the formulas are the same which are used. So a string whose length changes when forces are applied to its end is said to be elastic. The length of the string when no force is acting is known as the natural length, or what we call original length. In order to stretch an elastic string, equal and opposite extending forces must be applied outwards to the ends of the string. So if this is a string, you apply a force going this side and a force this side. Those are equal and opposite. The string is then in tension and exerts an inward pull. So the tension, like you have always known, tension arrows must face each other. So that will be the tension in the string, and this will be the pulling force. Equal in magnitude to the extending force. The difference between the natural length of the string and the stretched length is what we call extension. For example, that is the string when no force is applied, and the length is called natural length or original length. We usually denote it with the letter L. Then when you apply a force and stretch it in between two fixed points, this and this, there will be tension in the string and the tension arrows. So always tension arrows must face each other. So this extra length is what we call extension. Here, I think realize that here there is nothing like tension, because tension only appears when there is an extension. tension appears when there is an extension. When there is no extension at all, there is no tension. Okay, then Hooke's law. Hooke's law, you also covered it in your O-level physics, but now we shall also need it here. So the relationship between T and X were conducted, this is O, were conducted by the English physicist Robert Hooke. This is the period in which he was alive. And he concluded that subject to experimental errors and provided elastic limit is not exceeded, that tension is proportional to extension. So this is the statement we need, which is here, T is proportional to X. Now to remove this proportionality sign, we have to add what we call a constant of proportionality. That's why you see T is equal to Kx, where K is the constant K in the above equation is frequently expressed in the form lambda over L. So what is lambda and what is L? L is, we have already known it, that's the original length. And lambda is, which we shall call it modulus of elasticity. Therefore, when we replace K with this, we are going to come up with this general equation, and this is the equation we shall be using always in this topic. So when they ask for tension, just know that's lambda x over L, modulus of elasticity, extension, original length. So with that, let's see how we can briefly use that equation which I've got so that it can stick in our heads. So question 1 says an elastic string whose modulus of elasticity is 18 newtons is stretched from its natural length of 1.4 meters to a length of 1.8 meters. Find the tension in the string. So first thing we need to get is the extension. So original length, new length. The difference between the two gives you the extension. Then modulus of elasticity there. So now that we have lambda, we have x, we have L, we can quote the formula and substitute and get the output. And that will be the tension they wanted. Then question 2, an elastic string of natural length 1 meter is stretched to a length of 1.3 meters by a force of 3 newtons. Find its modulus of elasticity. So still shall come and first interpret the question. Original length, pulling, stretching force is that. Then new length is this, meaning you can get extension. The difference between the two gives you the extension. And now that we have L, X, and F, which is tension, we can easily get the modulus of elasticity. So come and substitute for F, for X, and for L. Then look for a way of making lambda the subject. It will be 10 newtons. Then question 3, a force of 8 newtons acts outwards at each end of a light elastic string. Note this word, each end. There's some trick there. Of natural length 1.6 meters. Find the stretched length of the string if the modulus of elasticity is 20 newtons. So we have the original length, we have the modulus of elasticity. Therefore, the net stretching force, remember they said it is stretched at both ends, meaning that the total stretching force will be 8 plus 8. That was the trick which was there. Then you can come and code the formula, substitute, and make X the subject. Therefore, the stretched length will be original length plus the extension. Question 4. An elastic string of natural length 3 meters and modulus of elasticity 15 newtons. Find the extension in the string when the extension is tension in the string when the extension is 40 centimeters, and Roman 2, extension in the string when the tension is 3 newtons. So one is that the units should be in SI unit. So this was 10 meters, we have to convert to meters. Then you can code the formula, substitute, and get the output. That was Roman 1. Then Roman 2, that's what we are given. So you code the formula, substitute for T, for lambda, for L, and make X the subject. Question 5. A light elastic string whose natural length is 0.8 meters is stretched to a length of 1.1 meters by a force of 12 newtons as shown. Okay, find the modulus of elasticity. So still here they are given us the force, stretch length, and original length. When I subtract the two, I'll be able to get the extension. Then I will code the formula, substitute, and make lambda the subject. Then question 6. One end of an elastic string of natural length 1.2 meters and modulus of elasticity 20 newtons is fixed to a point A on a smooth horizontal surface. A particle of mass 1.2 kilograms is attached to the other end B, and a force acts on the particle, pulling it away from A until the length of the string has increased to 1.5. Roman 1. Find the tension in the string. Roman 2. If the force ceases to act on the particle, find the acceleration with which the particle begins to move. And Roman 3, state with a reason whether or not the particle continues to move with constant acceleration. So the previous questions 1 to 5 have been where to make you well versed with the formula of T equal to lambda x over L. Now we have to see how to apply it in a more advanced way, the questions which are examinable. So now let's get started. 1, they didn't draw for us a sketch, but we need a sketch. So we shall come and first make a sketch, get a horizontal surface, get a fixed point, that is the string, that is the stretched particle, stretched by a certain force F. And because it is stretched, there will be tension in the string. This will be the original length plus the extension. The extension will be the new length minus the original length to give you extension. Therefore, you can come and code the formula T is equal to lambda x over L to give you the tension in the string. Then Roman 2, if the force ceases to act on the particle, find the acceleration with which the particle begins to move. Remember, it was stretched. Now when you release it, it has to move towards the side. Now they're asking, with what acceleration will it begin to move? Not the word begin to move. So when the force is removed, the only horizontal force acting on the particle is the tension in the string, and this acts towards A, meaning the particle moves towards A. So let's redraw and show the direction of the acceleration on the particle. Tension, then the acceleration. Remember, we are saying the acceleration with which it begins to move. So using F equal to ma, force is this tension, then the mass is this, meaning I can get the acceleration, and that's what they wanted. Then Roman 3, they're asking, state with a reason whether or not the particle continues to move with constant acceleration. So what do you think? Now, as soon as the particle begins to move towards A, the string gets shorter and the tension in it keeps on reducing. Why? Because the extension has reduced. Remember this formula, this is a constant. So as this one increases, this will increase. But now when the particle is moving this side, x keeps on reducing, meaning tension must also reduce. And because tension reduces, when this value reduces, it means that this one will also reduce. Therefore, the particle does not move with constant acceleration. That was strings. Now we shall go to springs. Remember, we say the main difference between string and a spring is that a string is only stretched, but a spring can be compressed as well as stretched. So for strings, we are using just a straight line, but for springs, we have to use this symbol. Now, this is a string at its original length, L, meaning there's no tension and there's no thrust. Now there's a new word which has appeared, thrust. We have been used in strings, we are used to what we call tension in the string. But now we bring in the word thrust. What does it mean? Thrust, okay, let me do like this. When stretched, the force in the string is called tension. But when it is compressed, the force in the spring is called thrust. So when they say find the thrust in the spring, it means that the spring was compressed. When they say find the tension in the spring, it means the spring was stretched. That is the only difference. So that will be the original length. Let us try to compress this spring. What will happen? So when you compress, that's what we get. It means that the new length is now smaller than the original length. And there is thrust in the spring. And this difference is what we call the compression. Now you know the difference. Thrust, in tension, the arrows were facing each other. In thrust, in compression, or in thrust, the arrows face away from each other. So each time a spring is compressed, always remember to show the arrows in this form. They face away from each other. What about if when it is stretched? One is that the length increases. And there is tension in the spring. So it has been stretched by distance x. So here, when you see the arrows facing each other, it means there is tension. So the same formula used to get tension is the same formula used to get compression. Sorry, the same formula used to get thrust. So you shall not write a new formula. We shall still stick with the one we used for strings, which is this. So let's also go through some few questions on springs. for you to master the formula. So question 1 says, a spring of natural length 1.5 and modulus 25. Find the thrust in the spring when it is compressed to a length of 1.2. So one, we have to get compression, the difference between the two, which is that. Then we code the formula, substitute, get the output. That will be the thrust. Then question 2, an upper body exerciser consists of a spring of length 20 centimeters with a handle attached at each end. The modulus of elasticity of the spring is 600 newtons. A boy can stretch the spring to 25 centimeters in length. Find the force which he is then exerting on the handle. So first is to interpret. You are given that the modulus of elasticity is 600. The original length is 20 centimeters. We convert to SI unit. Then the extension will be the difference between the new length and original length, which is 5 centimeters, and we convert to meters. Then you can code the formula, substitute, and get the output which they wanted. Question 3. The natural length of a light spring is L, and its modulus of elasticity is lambda. Find in terms of L and lambda the length of the spring when Roman 1, the tension in the spring is this, and Roman 2, the thrust in the spring is that. So like I told you, both thrust and tension we use the same formula. So we shall come and code the formula, substitute tension, and then make X the subject, which is that. So tension means there was an extension, therefore the new length will be original plus extension to give you this. Thrust means there was a compression, so the new length will be original length minus the compression to give you that. And that's what they wanted. Then question 4, the length of a spring whose modulus of elasticity is 30 newtons is reduced by 0.4 meters when compressed by a force of 20 newtons. What is the natural length of the spring? So still first interpret. They said reduced by, so meaning that is the compression. So net compressing force is this, because on either side. So we shall come and code the formula, substitute, and make L the subject. Question 5. The natural length of a light spring is 0.9 meters, and its modulus of elasticity is 20 newtons. Two forces act inwards, one at each end of the spring. Find the compressed length of the spring if the magnitude of each force is 8 newtons. So interpret the question, then net compressing force, you add the two to give you this. Then you can code the formula, substitute, and make X the subject. Therefore, the compressed length is that. Okay, that was introducing you to springs and strings. So now that you know both of them, that we use the same formula, we can now go to a section called equilibrium of a particle. So we already covered equilibrium of a particle, which but in that case we are using inelastic strings, or what we call inextensible strings. But what if the string is elastic, what could you do? So that is what we're going to look at in this part. So consider an elastic string with one end fixed at A and the other end attached to a mass M, so that the mass M is suspended in equilibrium, as shown below. So we'll come and first illustrate the question, what we have said. So fixed at A and a mass is attached to the other end. So because of the weight, there will be tension in the string. And because there's tension, it implies that there must be an extension. I think you remember when a string is at its original length, there is no tension. Tension only comes in when there is an extension. So you come and say that the whole length has both natural length and the extension. Now we have been using X for extension. Why are we changing to E? So E is another word. E is better used when the particle is in equilibrium. But X will still be varied. We shall see as we proceed that these two words will be used. They can first will be in equilibrium, then they can say we stretch it a further distance. Now that further distance is what we shall call X. So E is extension in equilibrium, X is an extra stretched distance. But we shall see all that in this video. So resolving vertically, force this will be equal to this. Then from Hooke's law, tension can be given by that. Therefore, when I equate the two, I'll come up with this expression. Meaning that if I have mass, I have lambda, I have L, I can get E. So let's go through some questions. Question 1. A light elastic string of natural length 1 meter and modulus of elasticity 35 newtons is fixed at one end and a particle of mass 2 kilograms is attached to the other end. Find the length of the string when the particle hangs freely in equilibrium. So shall first make a sketch of the information given. Then shall put the forces. There is weight. Because of weight, there will be tension. Arrows must face each other. And because of tension, there will be extension, which is this. Then shall remember the resolving vertically, we get this. Substitute for G, you come up with that. Then from Hooke's law, T is given by that, meaning I'll substitute for T here. Substitute for modulus and also original length to get the value of E. So that will be the extension. But they said find the length of the string. So the length will be L plus E. So come and substitute and get the output. That's what they wanted. Question 2. A light elastic string of natural length 2A is fixed at one end A and carries a particle of mass 3m kilograms at the other end. Okay. When the particle is hanging freely, a horizontal force of 3 mg newtons is applied to it. Okay. When the particle is in equilibrium, the string is inclined to the vertical at an angle theta, and the extension of the string is A. Roman 1. Find theta. Roman 2. Show that the modulus of elasticity of the string is 6 mg root 2 newtons. So still we shall need to make a sketch. So that the sketch, there is original length and an extension. So we are told that the extension is A, and the original length is 2A, and that it will be inclined at an angle of theta to the vertical, the string. So these angles are equal because of alternating, the property of alternating angles. Then we shall need to show the forces. There is weight, which always acts vertically downwards. There is a horizontal force, which makes the string to be inclined at a certain angle. Then there is tension in the strings. Arrows must face each other. So now I can resolve. Resolving horizontally, I'll get t sine theta is equal to 3mg. What about resolving vertically? I'll get t cos theta is equal to 3mg. Those are two equations. Is it possible to divide the two? When I divide, I'll be able to eliminate the t. This will cancel, so I remain with tan theta equal to 1, meaning that theta is 45. And that's what they wanted in Roman 1. Then for Roman 2, they said, show that the modulus of elasticity of the string is 6mg root 2. So from equation 1, we know the value of theta is 45, meaning I can get t, which will be this. Remember, 45 is a particular angle, and sine 45 is root 2 over 2, or we can say 1 over root 2, and over the 2 is okay. So let's use 1 over root 2. So this divide by 1 over root 2, the root 2 comes up, that's why you see it here. Then by Hooke's law, for either portion of the string, tension will be equal to lambda E over L. So I've got tension, I know the extension, I know the original length, I can get the value of lambda, which will be that, and that's what they wanted. Question 3. Two elastic strings, AP and BP, are attached to a particle of mass 2 kilograms at P. Okay. The ends A and B are attached to fixed points, which are 135 centimeters apart, with A vertically above B. Okay. Each string has a natural length of 50 centimeters, and the moduli of elasticity are this and this. So this is for AP, this is for BP, respectively. If the system hangs in equilibrium with the strings in the same vertical line, calculate the extensions in the strings. So first we shall need to make a sketch. There are 2 points A and B. Then they attach a string from A to B. So this is string AP and this is BP. The particles in between. So each one has an extension. So let this one be extension E1, and then this one the extension let it be E2. Because of extension, there will be tension. Now there's something funny. Do you see here? Here it is okay. Tensions are the same, T1, T1. But here there is this other 2G which has been added. Why is it that here we have 2G plus T and here we have only 2T2? It is because this particle also has a mass, and each time wherever there is mass there should be weight. So there is this T2 to counteract this, but also there is this weight of 2G. So because both are acting downwards, I've chosen to add the 2. So at equilibrium, upward force are equal to downward force. So come and use these forces. So you come and substitute for T1 and T2. Lambda 1 E1 over L1. Lambda 2 E2 over L2. Then we come and substitute. Here is for the first one, lambda is this. For the second one, lambda is that. Then the original length are all 0.5. There is this and also that. Then this is a constant. So when I simplify, I'll come up with equation 1. Okay. Then I'll remember that they told us something. The 2 points are 135 centimeters apart, meaning from here up to here is 135 centimeters, which is 1.35 meters. Therefore, E2 will be equal to 0.35 minus E1. Now I have 2 equations and 2 unknowns I can easily solve. So substituting equation 2 into equation 1, I'll come up with this. Then expand and collect like terms and get the value of E1. Now that I've got E1, I can get the value of E2. Then question 4, a particle of mass m is attached by means of light strings AP and BP of the same natural length A and moduli of elasticity this and that, respectively, to points A and B 3 m apart on a smooth horizontal table. The system remains in equilibrium with the strings in the same horizontal line. Find the extensions in the strings. So the previous question was about when the strings are vertical. What if they are horizontal? So that is it. There will be both original length and extension. Extension and original length. Because of extension, there will be tension in the string. So at equilibrium, here, this will be equal to this, which is here. Then from Hooke's law, T1 is that, Hooke's law, T2 is that. Then substitute for this and this. Then this and this. So I can simplify this cancels to remain with E1 is equal to E2. But the distance apart was 3a, so all this must be equal to 3a. So from there I'll come up with this. E1 plus E2 is equal to a, but we know that E1 is this, so while there was E1 I've put there to E2. Then collect like terms and make E2 the subject. Then because we know E2 we can get E1, and that's what they wanted. Question 5. A particle of mass 1.5 kilograms lies on a smooth horizontal table and is attached to 2 light elastic strings fixed at points P and Q, 12 meters apart. The strings are of natural length 4 meters and 5 meters, and their moduli are lambda and 2.5 lambda, respectively. Show that the particle stays in equilibrium at a point R midway between P and Q. So we shall come and make a sketch. We have point P, we have point Q, and there is a particle in between. So they want us to show that this R is the midpoint of P and Q. In other words, PR, distance PR is equal to distance RQ. So each one has an extension, original length and extension. Extension, original length. Because of extension, there will be tension in the strings. So at equilibrium, T1 is equal to T2. By Hooke's law, T1 is that, Hooke's law, T2 is that. Then substitute this one, the modulus is lambda, and this one is 2.5 lambda. Here original length is 4, here original length is 5. So simplify, you come up with equation 1. But they said distance apart is 12. So when I add all these ones, I'll come up with 12. Simplify and substitute. Here we substituted for E1. So that means I can get E2, and because I have E2, I can get E1. So I have to get distance PR, which is 4 plus E1. Then also distance RQ, which is 5 plus E2. Because they are the same, it implies that R is the midpoint of P and Q. And that's what they wanted. Question 6. The natural length of a light elastic string AB is 2.4 meters, and its modulus of elasticity is 4 G newtons. The ends A and B are attached to 2 points on the same level and 2.4 meters apart, and a mass m kilograms is attached to the midpoint C of the string. When the particle hangs in equilibrium, each half of the string is 60 degrees to the vertical. Find the mass of the particle. So I need to make a sketch. There are 2 points A and B. The particle is attached at the midpoint. Now note that it is still the same string. So if it is still the same string, tension has to be the same. They said it makes an angle of that to the vertical, which is this. So AB was 2.4, so it divides into 2. Why is it dividing into 2? It is because this length is equal to this, meaning this will be the midpoint of AB by geometry. Then we have weight. Here we have original length and extension. Then we have tension. So we already say that tension will be the same. So even here it will be T. So from triangle ACD, sine 60 is equal to opposite over hypotenuse. So AC will be given by that, meaning I can now get the extension. But they want the mass of the particle, meaning we have to resolve. So by Hooke's law, for either portion, T is equal to that. So substitute for this, and for that. It gives you the tension as that. So when I resolve vertically, I'll come up with 2T cos 60 is equal to mg. Substitute for T, G, and remain with M as the only unknown. So make M the subject, you'll come up with that, and that's what they wanted. Question 7 came from UNEB of 1994, paper 2, question 4, and it says, strings AC and BC are both of natural length 5L. AC is inelastic. Note that word. BC has modulus of elasticity lambda. A and B are attached to points on a horizontal line, distance 5L apart. A mass capital M is attached to C and the system is in equilibrium in a vertical plane with BC of length 6L. Find lambda and the tensions in AC and BC. So there are two strings, one is inelastic, the other one is elastic. In equilibrium, the one which is elastic, the stretched length will be 6L, meaning that if original length is 5L, it implies the extension will now be L, as simple as that. So let's first illustrate. So we have 2 points A and B separated by distance 5L, so AB is 5L. Then SC is also 5L because it is inelastic. Then BC is 6L. It has been stretched. Then we have weight, and because of weight there will be tension in the strings. We need to resolve, so we need to get some of the angles, so that be θ1 and that one be θ2. So by cosine rule, we have to look for getting these angles. So by cosine rule, I can say 6L. If I use 6L, 6L is this. It will be, we shall now be able to get this angle θ1. So simplify and get θ1. You can either get the angle direct or you can use Pythagoras identity to get the value of sine theta, because our interest is sine and cos when we are resolving. Then do the same cosine rule. I want to get this angle, so I'll use this. Then we shall simplify to get also cos theta, and also use Pythagoras or use a calculator to get that value. Then you can resolve horizontally. We shall come up with this equal to this. Then we substitute for cos theta 1 and cos theta 2 to get that as equation 1. Then resolving vertically, we shall come up with this. Then substitute for sine theta 1, sine theta 2, and g. But we know that T1 is this. So come and substitute for T1. Then collect like terms and get the value of T. Then the value of T1 will also be this. So M will be left in the question. For string BC, we know that T2 is equal to lambda x over L over L1. So come and substitute tension lambda x L1, original length. That means that lambda will be this. So now we shall go to question 8, which came from UNEB 1988, paper 2, question 7b, and it says, two springs AB and BC are joined together end to end to form a long spring. Okay, the natural length of the separate springs are this and this, and their modulus of elasticity are this and this respectively. The end A is fixed and the combined spring is stretched by 1 meter. Stretched by 1 meter. Know that word. Find the tension in the springs. So I need to make an illustration. So we shall have 2 points A and B. We shall have spring AB and also spring BC. They are stretched, so there is a force pulling. Let it be F. So this one has both original length and extension. Also, this one has both original length and extension. But remember, they told us stretched by 1 meter, meaning this E1 plus E2 must be equal to 1. So this will have tension. Remember, it's tension, the arrows must face each other. Also here, there's tension, arrows must face each other. So that's what they gave us, stretched by 1 meter. When I make E1 the subject, I'll come up with E1 being equal to 1 minus E2. Then for series arrangement is this kind of arrangement. Where one stops is where the other starts from. The tensions are the same. I think you can get it from here. This is equal to this. Therefore, by Hooke's law, T1 is that, T2 is that. Then come and substitute modulus, extension, original length. Then cross multiply and simplify to get E2. So it will be that. I know that E1 is given by this, so I can get my E1. But they asked for tension in the springs. So I can choose any. So if I choose T2, I'll come up, substitute for lambda 2, E2, and original length to get this tension. And that's what they wanted. Then question 9 came from UNEB of 2003, paper 2, question 6, and it says, a spring 8B of natural length 1.5 meters and modulus lambda Newton is fixed at A and hangs in a vertical position. The other end is joined to a second spring BC of natural length 1 meter and modulus 2 lambda. A particle of weight 15 Newton is then attached to end C of the second spring. When the system is hung freely in equilibrium, the distance SC is 4 meters. Find the value of lambda. So still we shall make a sketch. There is one spring, then another spring BC. Now this one has a mass attached. Therefore there will be weight, which is 15 newtons. Because of weight, there will be extension in each spring. Original length, extension. Even here, original length, extension. Then there will be tension in the springs. Tension arrows must face each other. Tension arrows must face each other. Then you can start for series arrangement. T1 is equal to T2. You can see it from here. Then Hooke's law gives that, Hooke's law gives that. Then we substitute original length, modulus, to get equation 1. But we know that the distance apart is 4 meters. So we shall come up with E1 plus E2 being equal to that. Then substitute for E1 to get E2 as this. So now that we have E2 and they want the value of lambda, I can use this. So T2 will be equal to this, and this T from here, you realize that T2 is equal to 15. Therefore, substitute for lambda, extension, original length. So I can get the value of lambda, and that's what they wanted. Okay, so that has been a range combination of two strings. What now shall go to what we call energy. So when a string or a spring is stretched, energy is stored in that string or that spring. And that energy stored is called elastic potential energy. So elastic potential energy is a property of stretched strings or springs or compressed springs. The end of a stretched elastic string will begin to move if released. The string therefore possesses potential energy due to its elasticity. The amount of elastic potential energy stored in the string of natural length L and modulus of elasticity lambda when it is extended by an extension x is equivalent to the amount of work necessary to produce the extension. Therefore, in short, so this formula can be derived by that the derivation is in physics. For math, we need to only quote the formula. So elastic potential energy is lambda x squared over 2L. And it is never negative. So now shall use that formula to see how to answer these questions. Question 1 says, it came from UNEB of November 1998, part 2, question 6, and says, an elastic string of natural length 1.2 meters and modulus of elasticity 8 newtons is stretched until the extending force is 6 newtons. Find the extension and the work done. So I think you still remember this formula. We come and substitute and get the value of x, which will be the extension. They also ask for work done. Work done is the elastic potential energy, like I told you. So lambda x squared over 2L. Substitute for lambda x L to get this, and that will be the work done. Question 2 came from UNEB of 1996, part 2, question 11b, and it says, a smooth surface is inclined at 30 degrees to the horizontal. A body A of mass 2 kilograms is held at rest on the surface by a light elastic string, which has one end attached to A and the other to a point on the surface 1.5 meters away from A up a line of greatest slope. Okay. If the modulus of elasticity is 2g newtons, find its natural length and hence the energy stored in the string. So here there is an inclined plane. Let's first make a sketch. Then we have a fixed point and a string attached to a particle. That particle has mass, meaning we shall get weight. So the forces acting, there will be weight. Then we resolve it parallel to the plane to give this, and also perpendicular to the plane to give this. I think you realize that the forces, these ones are dotted. Then there will be normal reaction R and the tension in the string. Then the acceleration, when it is released, it will move up. Why? Because currently it was stretched. So resolving parallel to the plane, T is equal to this force is equal to this. Then substitute Hooke's law gives you that. Then 2 sine 30 gives 1. Then you remain with only G. So when I substitute for this, lambda, x, and L, I remain with L as the only unknown, then make L the subject. So that is the natural length, but they also ask for energy stored. So energy stored is lambda x squared over 2L. So lambda extension is 1.5 minus original length. Then L here to give you 1 joule as the energy stored. That was making you confident with how to use elastic potential energy. But there is also the principle of conservation of energy in elastic strings or springs. So we can now introduce potential energy of an elastic string into the principle of conservation of energy. Remember previously in the topic of work, energy, and power, the principle of conservation of energy was we're interested in only two forms to make up mechanical energy, and that was potential energy and kinetic energy. But now here in elastic strings and springs, because there is some energy stored within the string, we add on that component of energy which is stored within, and we call it elastic potential energy. So in this case now, total energy is given by three parts: gravitational potential energy, elastic potential energy, and kinetic energy. But the principle still remains the same, that initial total energy is equal to final total energy. Now let's see how this principle is used. Question 1. A particle of mass, so the question is a little long, but that shouldn't scare you. So read it and understand it, then we shall be able to answer it. So a particle of mass 2 kilograms is attached to one end of an elastic string of natural length 1 meter and modulus of elasticity 8 newtons, which is lying on a smooth horizontal plane. Okay. The other end of the string is fixed to a point A on the plane, and when the string is just taut, taut is another word to mean tight, the particle is at a point B. The particle is pulled away from A until it reaches a point C, okay, where AC is 1.5 meters and is held in that position. Okay, part A, find Roman 1, the initial energy stored in the string when the body is at point B. Okay, Roman 2, the energy stored when the body is at point C. Okay, part B, the particle is then released from rest at point C. Find Roman 1, the acceleration with which the particle begins to move. Roman 2, the kinetic energy of the body as it passes through point B. Roman 3, the velocity of the particle when it passes through point B. So let's begin. We shall begin by making a sketch of the information given. So they talked about 3 points. There is a point A, point B, and point C. Point A is the fixed point. Then B is the point where the string is just tight but not yet extended, not yet stretched, meaning that AB is the original length. Then beyond point B to point C, there is an extension. They told us that SC is 1.5. So the extension will be 1.5 minus the original length to give you 0.5. Because of the extension, there should be tension in the string. Some point it was released. When it is released, it will move with an acceleration A. But for part A, it was not yet released. So they start answering the question. One, they ask for energy stored when it's at point B. initial energy stored in the string when the body is at point B. Now there is something funny about this point B. Do you know something? At point B, extension is 0. And because the extension is 0, energy must be 0. Okay, what about at point C? At point C, there is some extension. Therefore, there is some energy stored, which is 1 joule. Then now part B. Part B, they said, let's see. The particle is then released from rest at point C. Okay. Find the acceleration with which the particle begins to move. So at that point, we know that Hooke's law, we can get the force. After getting force, we use F equal to ma to come up with the acceleration they wanted. And that's what they wanted. That was Roman 1. Then Roman 2. The kinetic energy of the body as it passes through point B. And also Roman 3. The velocity of the particle when it passes through point B. Okay. That means that there we shall need to use conservation of kinetic energy. Sorry, conservation of energy. At this point and at this point. So total energy at point B is equal to total energy at point C. At point C, there is an extension, meaning there is elastic potential energy. The good thing we have already got it here. And at point B, there's no extension, so elastic potential energy is 0. So let's use that knowledge. And remember, it was released from point C, meaning velocity at C is 0. So kinetic energy at C is 0. Now, why isn't there potential energy here? Remember we said total energy has 3 parts. There is gravitational potential energy, elastic potential energy, and kinetic energy. Now, gravitational potential energy comes into play when we are dealing with vertical motion. But now here it is entirely horizontal, meaning there is no change in height. So kinetic energy at point B, elastic potential energy at point B is 0, kinetic energy at point C is 0, elastic potential energy at point C is 1. So kinetic energy at point B is 1 joule. But they also ask for velocity. We know that kinetic energy is a half mv squared. So come and substitute for m and for kinetic energy. You'll be able to get the value of V. And that's what they wanted. Question 2. A body of mass 5 kilograms lies on a smooth, this is a smooth horizontal table and is connected to a point O on the table by a light elastic string of natural length 1.5 meters. The modulus of elasticity, this. Initially, the body lies at point P, 1.5 meters from O, and is held at point Q, 2.5 meters from O, and then released. Find Roman 1, the initial energy stored in the string when the body is at point P. Okay. That Roman 2, the energy stored in the body, when the body is at point Q. Okay. Roman 3, the acceleration with which the particle begins to move. The kinetic energy of the body as it passes through P after being released from point Q. Then the velocity of the particle when it passes through point P after release. Okay, so first we need to make a sketch. Horizontal surface, then fixed point, and the particle being stretched. So there are 3 points. There's point A, there is point P, which is the original length, and then point Q, which is the extended length. So now here they told us the stretch length is 2.5 and original length is 1.5, meaning extension will be got by subtraction. Then there is tension in the string and also acceleration when released. So let's start with Roman 1. They said the energy stored in the string at point P. I think you remember from question 1, when there's no extension, energy is 0. So here energy will be 0. Then at point Q, extension is 1, so there will be energy stored. Then Roman 3, they want the acceleration with which the particle begins to move. So we use F equal to ma, but before that, we shall first get T. We shall first get the force, which is tension, using Hooke's law. So now that we have got the tension, we can now use F equal to ma to get the acceleration with which it begins to move. Then Roman 4, they wanted the kinetic energy at point P, so by conservation, we have that. Then we substitute and get the kinetic energy they want. Then Roman 5, they wanted the velocity, so remember that kinetic energy is half mv squared. Substitute and get the value of v. And that's what they wanted. Question 3. A particle of mass 5 kilograms is suspended from point A by a light spring of natural length 0.4 meters. When in equilibrium, the particle is at point B, vertically below A, where AB is 1.8 meters. The particle is pulled down to point C, also vertically below A, where AC is 3 meters. It is then released from rest at C. Roman 1. Find the modulus of elasticity. And Roman 2. Find the speed of the particle as it passes through B. So shall I need to make a sketch. That is the fixed point, the point A. Then there is a spring with a mass attached and it's in equilibrium at point B, which is this. And the distance here, it was AB, which is 1.8. So there is weight. The mass was 5 kilograms. So weight will be 5g. Because of weight, there will be tension. For tension, arrows must face each other. But they told us the particle is pulled down to point C. So I'm going to pull it further. So there is still tension, but the tension changes because the extension has changed. Now here it is split. There is original length, there is extension at equilibrium, which is E. And there is also the extra extension, which is now called X. I think, remember I told you, at equilibrium we use E, then the further distance stretched will be called X. So now I can say at equilibrium, it means I'm going to use this, which is T1 is equal to 5G. Substitute T1 is that, equal to 5G. Then substitute for extension and original length and G to get the modulus of elasticity. And that's what they wanted in part A. Part B, they said find the speed of the particle as it passes through B. When you hear the word speed, it means that you have to conserve energy. So we are going to use 2 points. There is point B and point C. And now here it is vertical, meaning there is gravitational potential energy. So by conservation of energy, total energy at B is equal to total energy at C. So we have kinetic energy, gravitational potential energy, elastic potential energy at both points A and C. Then we shall substitute. For kinetic energy, it's a half mv squared. For this one, it is mgx. For this one, it is lambda e squared over 2L. Remember, it would have been lambda x squared over 2L. That's what we derived. But because there it's in equilibrium, we use E instead of X. Let's see in the diagram. So when the lowest point becomes the reference when you are getting the gravitational potential energy. Therefore, at point B, the height is X. That's why we used mgx. Here it passes B with a certain velocity V. That's why we used the half mv squared. Then the elastic potential energy, at this point, the extension in the string is E. That's why we use lambda e squared over 2L. What about at point C? At point C, the height is 0 because this is the reference line, meaning that potential energy will be 0. That is 1. 2, the particle was released from point C, meaning velocity is 0. Therefore, kinetic energy is also 0. 3, elastic potential energy, the total extension is E plus X. So that is what we use to get the elastic potential energy. So that gives us the statement here that K is here 0, P is 0, elastic potential energy is that. So we shall substitute for mass G, X, lambda, extension, original length, lambda, equilibrium extension, XY extension, original length. So you only have V as the unknown. Our work is to look for making it the subject. So collect like terms, simplify, and get the value of V. And that's what they wanted. Question 4. A body of mass 2 kilograms is freely suspended from a spring of natural length 75 centimeters and modulus of elasticity 6G newtons. The other end is fixed to a point A. The body initially hangs freely in equilibrium at point B. It is pulled down a further distance of 25 centimeters to point C and released from rest. Find part A, the distance AB, part B, the energy stored in the spring when the body rests at B. C, the kinetic energy of the body as it passes through B after release from C. So still first we shall need to make an illustration. So that is at equilibrium. Here we have original length plus extension. Then you have the weight of the particle. Then the tension, arrows facing each other. Then it was stretched a further distance to point C. So we still have tension in the string, but they are changed because of extension. Then you have the original length, the equilibrium extension, and the extra distance moved downwards. Okay. So now we shall start with part A, distance AB. They want distance from A to B, which is this. So how can we get the extension? T is equal to 2G. So Hooke's law, T is that, equal to 2G. Then substitute for this. They told us that modulus of elasticity is 6G. And over L times 2G. Meaning I can get the extension. After getting the extension, I can get the distance, which is L plus E, and it is 1. Part B, they said the energy stored in the spring when the body rests at point B. Here the extension is E, so the energy will be lambda E squared over 2L. Substitute and get the output. Part C, the kinetic energy of the body as it passes through B after release from C. So there we have to conserve energy. Total energy at B is equal to energy at C. This equal to that. Then we substitute. We know M is that, G is that, X is that. And here we know lambda is the whole of this, E is that, X is that, L is that. So I can simplify and make KE the subject, and that's what they wanted. So that brings us to the end of this video. Thanks for watching, and be reminded the next video will be on simple harmonic motion. So if you have not yet subscribed, please click on the subscribe button below this video so that you can receive updates when the next video has been uploaded. And also, if you know any student who's not yet on this platform, please share the link of this video with them via social media platforms like Facebook and WhatsApp, so that we can all benefit as a family.